In this video, we're going to go over numbers 27, 29, and 31 in chapter 16 in the thermodynamic chapter. So I'll try to sort of have the book sheet here for a minute, and then we'll go and work the problem. So 27 says, given the values of delta H and delta S, which of the following changes will be spontaneous at constant temperature and pressure? Okay, so you learned in the reading that a spontaneous process, the Gibbs free energy is going to be negative. When delta G is less than 0, you have a spontaneous process. And also in the reading, you got this formula that delta G can be defined using the equation delta H minus T delta S. Now there's a real big issue in this equation, and that is that delta H is almost always in kilojoules per mole, and delta S is almost always in joules per mole. Go figure. They couldn't get that to be the same, right? Would have been a lot easier. So what I like to do is I'm going to convert my kilojoules to mole right away to joules per mole. Oh, and this is joules per mole Kelvin, I should say, the delta S. Okay, so what we're going to do is we're going to use the information in each part of this problem, and we're just going to calculate what's delta G. And if delta G is negative, it's spontaneous. Now, in some cases, you're going to be able to tell right away. So, for example, on the first one, A, we're given delta H is positive 25 kilojoules, and delta S is positive 5 joules per mole, joules per Kelvin. So these are all per mole, but they're not putting the mole on the bottom. And T is 300 Kelvin. Okay, so let's think about, and the video I think did a very good job of explaining this, that if delta H is a negative number and delta S is a positive number, T is Kelvin, and so T is always positive. This is always a positive number, you never have to worry. So whenever delta H is negative and delta S is positive, that's going to guarantee that delta G is negative. Okay, so if this is the combination, delta G is negative. Whenever delta H is positive and delta S is negative, well, a minus of a minus, right? A minus of a minus is a plus. That's going to guarantee delta G is positive. So you don't even have to do the calculations in those cases. So let's take a look at what we have here. We have delta H is positive. We have delta S is positive, so it doesn't fall into one of these two situations, so we're going to do the calculation. So we're going to say 25,000, right, joules, because I'm going to convert that to joules right away, minus 300 Kelvin times 5 joules per Kelvin. And so the Kelvin cancels, right? That's why now we have both of these are in joules, if I put my joules on. And so this becomes 25,000 joules minus 1,500 joules. Well, that's a positive number. And so this is not spontaneous. So 27, you would get a delta G is positive, and it would not be spontaneous. For part B, we have delta H is positive 25 kilojoules. Right, so I'm going to say 25 times 10 to the 3 joules, just to use scientific notation. We have delta S is positive 100 joules per Kelvin, and this process is taking place at T is 300 Kelvin. Okay, so I'm going to look at my known availability. If delta H is positive and delta S is positive, I'm not in one of the known cases, so I'm going to have to do the calculation. So delta G is equal to 25 times 10 to the 3 minus 300 times 100. And when I do that, I get minus 3 times 10 to the 4. So I can say this is 2.5 times 10 to the 4. Remember, if this goes down, divide by 10, the power of 10 goes up. And that's going to come out to be negative. 2.5 minus 3 is a negative. That would equal negative 0.5 times 10 to the 4, which is 5 times 10 to the 3, 5,000. And so delta G is negative, and so this is spontaneous. So B is spontaneous. A is not spontaneous. Okay, let's look at C. So for 25, on part C, we have delta H is negative, and we have delta S is positive. That's one of our situations. Delta H is negative, delta S is positive. That automatically guarantees delta G is negative, and so it is spontaneous. Part D, we have delta H is negative 18. Oh, sorry. Delta H is negative 10 kilojoules. And delta S is negative 40, so I'm not in one of my guaranteed situations. And T is 200 Kelvin, so we'll plug in delta G is equal to negative 10 times 10 to the 3 minus 200 times negative 40. Okay, so what do we have? We have negative 10,000 here. And then 200 times 40, well, 4 times 200 is 800, so this is 8,000, so we're going to plus 8,000, and I get minus 2,000, and since it's negative, delta G is negative 2,000 joules. That is going to be a spontaneous process. And that's how you do those calculations. Okay, so let's look at 29. Okay, so 29. Ethanol, also called ethyl mercaptan, I'm not sure how to say that, is commonly added to natural gas to provide the rotten egg smell of a gas leak. So it's not ethanol, it's ethanethiol. The boiling point of ethanethiol is 35 degrees Celsius, and the heat of vaporization is 27.5 kilojoules per mole. What is the entropy of vaporization of this substance? Okay, so let's talk a little bit about boiling point. I'm going to flip the page here because I'd like to remind us about these heating and cooling curves. So remember at the beginning when we first did thermo, we looked at heating and cooling curves, and we said when you're on this axis is the energy that you add, and this axis is the temperature, and a heating and cooling curve of a substance would look something like this. And as I put energy in, I can watch my substance go up this curve. And if I took energy out, I would watch the substance come down this curve. And this part, that first ramped part, sloped part, is a solid. This is melting or freezing, depending on which way you're going, because you're going from solid to liquid. And then this is the liquid phase, and then you're going from liquid to gas, so you're either vaporizing or condensing, depending if you're going one way or the other. And then this is gas. So when we talk about boiling point, we're talking about the temperature. So on this problem here, it says that the boiling point of ethanol, so I'll put T sub B, and I'll come back under the screen here. T sub B for ethanol is 35 degrees Celsius. And the heat of vaporization, so delta H vaporization, is equal to 27.5 kilojoules per mole. Okay, so how does this help us figure out what is the entropy of vaporization for the substance? So when we go, this is vaporization, so we're up here. So when we go from liquid to gas along this flat part, essentially what's happening is this much energy has to be added per mole. I have to change my energy by that much. That's what this number is. It's saying how much energy do I need to add in order to change 1 mole from a liquid to a gas. Okay, that's what the heat of vaporization is telling us. Now, we also know that when something goes from a liquid to a gas at its boiling point, at that temperature, it happens spontaneously. So if I have a pot of water on my stove, right, so I'm going to make some spaghetti, and I have my pot of water, and I have my flame on my stove, right, and I have water in it. When this water gets to 100 degrees Celsius, it boils, and it all turns into a gas. So at this temperature, it's a spontaneous process for that to turn into a gas. So when we talk about the boiling point, that's the temperature at which the substance spontaneously changes state. Right? Think about in the winter. At 0 degrees Celsius, water spontaneously turns to ice. I don't need to go out there and do anything to the ice, to the water. It will just turn to ice at that temperature. Okay, so what we're looking at is a delta G calculation. When delta G is 0, that is the, between delta G is negative and delta G is positive. right? So when delta G is 0, that's the threshold when a process will be spontaneous. And that's the case at boiling points. So at boiling points and freezing points, okay, so either one, melting points, freezing points, any phase change, that temperature gives you delta G is 0. That's what's happening, okay? And so we're going to use these and we're going to figure out what delta S is using, we know delta G is equal to delta H minus T delta S. Okay, now heat of vaporization. I'm going across my chart. I'm going to vaporize. I'm going in the positive direction. I'm adding this. So that's an endothermic reaction. So we're going to say 0 equals 27.5 times 10 to the 3 joules, because remember I want it in joules, minus 35 degrees Celsius. That needs to be Kelvin. So I'm going to add 273, and that's going to be 308 Kelvin. So minus 308 Kelvin times delta S. And that's what we're looking for. Okay, and so if I subtract my 27.5 times 10 to the 3, I'm going to write it out, 27,500 joules equals negative 308 K times delta S. So I'm going to divide by negative 308 Kelvin. And when you do that, you find that delta S comes out to be 89.3 joules per Kelvin. And technically it should be joules per mole Kelvin because that was per mole, the heat of vaporization, so that should have been per mole, and then there's a mole there. Okay, and that's how you do that. And look at, we went from liquid to gas, so delta S should be positive, and we ended up getting a delta S is positive because anytime you go from liquid to gas, your delta S of your system, of your reaction, should be a positive number. Okay, let's see, number 31. Going to look at number 31.